Hello, everyone. My name is Joe Barco, and I'm Senior Director of Workflow Marketing at Unchained Labs. I'll be your moderator. Thank you for joining us today. It's very likely you're already automating many of your laboratory processes and possibly looking to automate more. In case you're not, let's first discuss why we should automate, and I'll use this image as an example. Lab work has traditionally been very labor-intensive, with many of us trained to have spent hours, nights, weekends, mostly doing things like weighing out reagents, pipetting, checking the progress of a reaction, making buffers, whatever. When a reaction doesn't work, there's often a requirement to just set up more conditions, so it becomes a lot of manual work to do that. And then even when a reaction does work, getting it to work better might require even more conditions to be set up, which consumes even more material to get there. And last but certainly not least, setting up lots of reactions or scaling them up to large volumes requires more reagents that may be flammable or toxic or under pressure, which makes safety a key concern. The better way, of course, is to automate. Here I show the deck of one of our systems, the Big Kahuna, where we can fully automate a set of reagent preparation and synthesis. On this deck are powder and liquid dispense, a capping and decapping mechanism, and methods to set up, run reactions in different conditions, and to sample reactions in a 96-well format. Automating gives you the ability to standardize how reactions are set up, from dispensing to timing to sampling. It allows you to accelerate development by more efficiently setting up more reactions faster than a person can do manually. It allows you to save material by enabling the scaling down of reaction volumes while maintaining assay robustness, all of which taken together will allow you to increase the experimental area that can be studied. Several of our customers and collaborators have graciously agreed to share their experiences and expertise in lab automation with us. Today, we'll hear from Abby and Jay. Next Tuesday, Georg from Roche will speak on how they integrated their junior into their workflow. And on May 25th, Paul Clark will talk about Dow's approach to automation and how that has impacted their product development. We'll have a Q&A session at the end of the presentation today. To ask questions, all you have to do is click on the Q&A in the Zoom navigation bar at the top or bottom of your screen and type your question. We'll get to as many of them as we can. And if we don't get to you, we will connect you with the speakers for follow-up. Today's presentations will discuss new areas and approaches to optimization through machine learning, which will enable data-driven decisions to be made more efficiently while still exploring a large reaction space. Our first speaker today is Professor Abigail Doyle, the A. Barton Hepburn Professor of Chemistry at Princeton University. She obtained her PhD in catalysis and physical organic chemistry at Harvard in 2008 under the direction of Professor Eric Jacobson. She joined the faculty of Princeton that same year and is currently co-PI in the NSF CCI Center for Computer Assisted Synthesis, or CCAS, and the DOE Bio-Inspired Light Escalated Chemistry BioLec EFRC, which is Energy Frontier Research Center. Professor Doyle's talk today is entitled Development of Bayesian Optimization for Chemical Synthesis. Good morning, Abby.
Good morning.
Thank you for joining us, and the virtual floor is yours.
Thank you very much, Joe. And hopefully my slides are showing now. It's a real pleasure to participate in this, and thank you both for the kind introduction and for putting together this great virtual symposium. So I'm really pleased to be here and tell you about some of our recent efforts to develop machine learning software that chemists can integrate into sort of their daily practices for reaction optimization. And before I get started, I want to acknowledge the fantastic team that has participated in the research that I'm going to tell you about today. So this team was led by a postdoctoral fellow in my group, Ben Shields. He was joined by Marvin and Jesus, also in my group. And we're really fortunate to collaborate with two other groups of scientists. We'll hear later from Jay Stevens. He was working with June and Jake Janey at BMS with us on this team, as well as Professor Ryan Adams at Princeton and his student Farhan. So this is a fantastic group of scientists who were able to come together and start thinking about how we do optimization in the lab and whether we could improve how we do so through integrating machine learning with experimental chemistry techniques, as well as high throughput experimentation. Now, reaction optimization is ubiquitous in chemistry, whether you're thinking about multi-step synthesis of a life-saving medicine or preparing a new performance material, or in an academic lab like mine, engaging in reaction discovery. And the challenge with reaction optimization is that chemists are faced with considering hundreds of different dimensions to explore in the context of finding an optimal result. And these dimensions include both categorical variables like the identity of a catalyst, the structure of a reagent such as an acid or a base, an oxidant or a reductant, as well as continuous dimensions like concentration, temperature, light wavelength, intensity, pressure. Given time and resource constraints, chemists are only able to evaluate just a small fraction, right, of this space that's represented here. And so we turn to various tools in order to reduce that space to make the problem tractable. And typically, the tools that we turn to are comparisons to literature precedent, using our chemical intuition and mechanistic understanding, as well as simple sort of models such as design of experiments. Now, optimization problems are not unique to chemistry. And in the field of computer science, Bayesian optimization has emerged as a particularly effective way of optimizing, for example, hyperparameter tuning in machine learning models. And what Bayesian optimization allows you to do is to identify the global maximum in a few number of experiments by balancing effectively extrapolation to sort of areas of uncertainty exploration of areas of uncertainty and extrapolation of sort of known data. Given sort of how well Bayesian optimization has performed in computer science areas, chemists have also been drawn to Bayesian optimization and other active learning technologies for reaction optimization. And so I'll point you to some sort of really important results that have been developed in recent years from Klaus Jensen's lab, for example, Alana Sparaguzic's group, as well as Rodriguez and Bernarda's group in the area of active learning for reaction optimization. Despite these advances, we recognize that there were certain sort of gaps in being able to deploy machine learning, in particular Bayesian optimization for chemical optimization. And a few of these are shown here. So most of the examples of applying machine learning to reaction optimization had previously only dealt with optimizing continuous variables like concentration and temperature, but were not sort of effective for optimizing categorical variables like ligand identity or pre-catalyst identity. Nevertheless, these are often one of the most influential variables when we're starting to undertake an optimization campaign. And so something that we wanted to address in developing some Bayesian optimization software for chemists. Another gap that we identified is that there's typically very little cost with respect to time to setting up more than one reaction at once when we're doing optimization. And indeed, we often like to have flexibility, whether we're running a batch of 5 experiments, 10 experiments at a time when achieving reaction optimization. And this was not something that was available to sort of in current studies. And it requires that the machine learning software think sort of multiple steps ahead, almost like a chess, right, player in thinking about optimizing in batches rather than one experiment at a time. And then finally, from the perspective of a sort of a practicing experimental chemist, we wanted to ask, how does Bayesian optimization sort of compare to human chemists in optimizing a given reaction? And not only that, can it find the global max? And is it dependent on the start, right, and what experiments you initiate the machine learning algorithm? And so these are some of the questions that we wanted to address in developing software for chemical reaction optimization. Before I jump into some of our results, I want to just walk you through the general framework for Bayesian optimization in the context of a simple case for a chemical optimization. So let's consider we're trying to optimize a two-dimensional reaction where we're just varying concentration and ligand, where each of these points on this grid represents distinct combinations of concentration and ligand. And this is the search space that we've defined. And what we want to be able to do is identify the highest yielding conditions, which is defined by this surface on the right, which is what we call our objective function, or our unknown objective. We don't know how the yield relates to the concentration and ligand in this type of surface, but this is what we're trying to predict so that we can identify the highest yielding conditions. So we would start by defining the search space. Then we would initialize the optimizer by collecting some data. And we could use either data that's already existing, or we could choose data on the basis of an experimental design, such as for the precepts of design of experiments, or through random selection of data points to initialize. So the chemist would then run those 5 experiments and measure the yield, for example, of those reactions. So the next step would be then to fit that data that we just acquired using a model, what we call a surrogate model. And the key requirements for this model is it's going to allow us to make predictions and estimate variance such that we can apply an acquisition function to that response surface model to select the next experiments. And there are many different types of acquisition functions that we'll sort of discuss a few that we considered in this particular project. So the acquisition function will then propose a new experiment or experiments to evaluate. A chemist would then go in, run those experiments, collect the yields, and then the surrogate model would update. The acquisition function would select the next experiment to run. And this process would iterate until we find the optimal result, or resources are depleted, or we see that there's a leveling off of yield in this case. Okay, so from that little toy example, what you can see is that there are certain sort of key pieces of the Bayesian optimization anatomy. The first is the search space. And in our software and our approach, the idea is that the chemist gets to decide this, right? This is where our mechanistic reasoning about what dimensions are important sort of come to play, where we can define both continuous and categorical dimensions to look at, as well as what components within any given dimension to define the search. The second key piece of information is what we call reaction encoding. So we need to be able to describe the conditions in a computer readable format. And this is particularly important for the categorical dimensions like ligand structure or reagent structure. And there are a number of different reaction encodings that can be evaluated. As I'll show you, we've looked at just 3 in the course of our studies thus far. Likewise, there are many different response surface models. We considered a few. And finally, acquisition functions. And so in particular, to be able to choose among those different possibilities, the acquisition function, the response surface model, the reaction encoding, we turned to experimental data to train and then statistically compare the different possibilities for the Bayesian optimization software. So the particular data that we use for training the models shown here came from 2 publications from 2018, one from Pfizer looking at flow-based technology for the Suzuki cross-coupling reaction. It was one reaction that involved approximately 3,700 experiments that varied a number of different dimensions, in particular ligand, base, solvent, as well as the structure of the aryl halide or pseudohalide and aryl boronate. And then the additional data that we use for training and evaluating the Bayesian optimization software came from our own group and that we conducted in collaboration with Merck, where we evaluated, in this case, 5 reactions, approximately 800 experiments each along a few dimensions, additive, base, palladium pre-catalyst, as well as aryl halide. So it was this data that allowed us to tune the various possibilities sort of for the Bayesian optimization software and then compare among them. And when we did this, what we found is that the configurations highlighted in blue were the most effective in the Bayesian optimization software. So in particular, for describing the reaction encoding, we found that using quantum mechanical descriptors, so these are chemical descriptors that capture the steric and electronic properties of the categorical components like ligand, were the most effective as compared to Mordred descriptors and one-hot encoding. So one-hot encoding just identifies the presence or absence of components, but doesn't have any chemical sort of knowledge associated with that encoding. For response surface models, we found that a Gaussian process model was most effective. And then finally, for acquisition functions, we found that expected improvement was the most effective in sort of optimizing within the training data. So just to give you a sense of what these different acquisition functions, for example, look like, sort of show you a plot here of the chemical space of one of the reactions in the training data, where each of these different sort of clusters represents different sort of sets of conditions. And what you can see is sort of for an acquisition function that's sort of purely sort of exploitive of data. So it's focusing on the data that it has and trying to identify sort of higher yielding conditions nearby. It stays very close to sort of where the optimization is initiated. Whereas acquisition functions that are set towards exploration, so looking for areas of greatest uncertainty, you see that it covers quite a bit of the landscape of the search space. And so ultimately expected improvement, which sort of balances these two, is what we found to be the most effective. And here are some of the statistics in comparing these different acquisition functions. Okay, so with all of that training, we sort of ultimately put together an open access sort of software package for reaction optimization. You can find it on GitHub here, and you can use the preset settings that we found were optimal from our training data, or you can sort of, it's flexible in terms of your choices of surrogate models, acquisition functions, and reaction encoding. And importantly, it can allow chemists to select the number of experiments they want to run per batch for optimization as well. Okay, so now with having trained the Bayesian optimization software, we wanted to assess its performance on a completely new reaction. And to do this, we ran high throughput experimentation in collaboration with Jay and BMS, wherein we evaluated this palladium-catalyzed CH arylation reaction, which is a reaction of importance to sort of BMS, given some sort of prior work that they've done applying this reaction to sort of multi-step synthesis of pharmaceutical ingredients. So we evaluated a search space of 1,700 experiments that comprised a few different dimensions: the ligand identity, base, solvent concentration, and temperature. And here are the various components that we evaluated for base, solvent, temperature, and concentration. These were chosen in part based off of prior knowledge of this reaction, as well as some sort of early experimentation that we did to make sure that we would see diversity and response, in this case for yield. And importantly, for sort of choosing the phosphines, what we did is we sort of surveyed the monodentate phosphines that BMS has available. We then featureized them using the DFT features and plotted the space and chose a selection of 12 phosphines that were sort of maximally diverse within this phosphine space. So from this, we collected this data. We then wanted to ask not only how does the Bayesian optimization perform within this data set, this new reaction, but also how would chemists optimize this reaction. And so in order to do that, we sort of put together an online game wherein we presented the same search space for the HTE work to chemists, and then asked them to optimize the reaction, choosing 5 conditions at a time. And so they would choose 5 conditions. Then the game would return the results from the HTE data set for those 5 conditions. And chemists would get to choose the next 5 conditions that they would want to run and to iterate over sort of 20 iterations total, so a total of 100 experiments. Now, finally, then we wanted to compare the two. And so what we did, since we had 50 chemists play the game, we ran the Bayesian optimization 50 times, where we started with a random selection of 5 experiments for each iteration of the Bayesian optimization. And so I'll just point out a few sort of things that we found in the Bayesian optimization case. I think the first thing to note that we were very excited about is within the experimental budget. So within approximately 15 batches of 5 experiments, every example, so every one of the 50 iterations found the optimal results in this HT data set. And in many cases, the Bayesian optimization found that optimal sort of in fewer batches than that. So you can see here the dark black line is the average of those 50 iterations, whereas the gray dashes are each of the individual optimization platforms. Now, compared to the chemists, there were a couple of interesting comparisons that we saw. The first one was that the average initial choices of the 50 chemists who participated was higher yielding than that of the Bayesian optimization software by about 15% yield. And that makes a lot of sense, right? Chemists, many of the chemists who participated had 10 years or more of experience as chemists. And so they bring with them knowledge that allowed them to choose, on average, a higher yielding set of conditions for that initial choice. But what we also saw is that within 3 batches of 5 experiments, the Bayesian optimization software outperformed the human participants on average. And the other thing that we noticed is that many of the human participants sort of stopped early in the optimization game. We don't know, can't sort of say exactly why that may be, but in many cases it may have been because they thought they'd identified the highest yielding conditions within the HT data set, which, I think perhaps comes to play because in this case, and this was not by design, what we found is that the optimal ligand for the CH arylation reaction is one that had never been published before. And so I think this presents an interesting case where, while chemists have great intuition that can allow them to sort of make initial choices that are higher yielding than what one would get from a random selection of experiments, we may also, that same intuition may come with biases, right, that lead us to not explore areas of chemical space that we might, that might sort of prove useful. In this case, it did. Whereas the optimization software, because it can allow for exploration of space in a statistical way, can allow you to identify, in this case, that global optimal result. Okay, so I'm going to end here and turn over the floor to Jay, who can tell you about some additional applications of this software. But I'll just conclude by saying that what we found is that applying the Bayesian optimization software to this particular problem, we were able to identify the optimal result in less than 2% of the chemical space. And I think importantly, sort of integrating this into everyday practices could allow chemists to explore a much larger space than we would otherwise be able to do on the experimental budget that we typically give ourselves for optimization. So I'll finish again by thanking the coworkers who have collaborated and worked on this project. I'll in particular point out, I'm very grateful for funding from the NSF, Center for Computer Assisted Synthesis, and Bristol-Myers Squibb through the Princeton Catalysis Initiative for this project. And at the end of this session, be happy to answer any questions.
Thank you, Professor Doyle. Sorry for jumping on a moment too soon. Thank you for walking us through how you developed and tested the optimization software. Next speaker, as Professor Doyle said, is Jason Stevens, who is the computer-assisted synthesis lead at Bristol-Myers Squibb. Jason obtained his PhD in the laboratory of Professor Michael Crimmins at UNC Chapel Hill. He followed his PhD with a postdoc in the laboratory of Professor McMillan at Princeton, joined BMS in 2012 as a process development chemist before moving to the high-throughput experimentation group in 2016. In 2020, he began a new role in the computer-assisted synthesis lead in the technology group at BMS Process. Today, Jason will talk us through the technical and logistical considerations for deploying EDBO in his talk entitled Lab Automation Leveraging Bayesian Optimization for Chemical Process Development. Good morning, Jay. Thanks for joining us. And begin when you're ready.
Okay, thanks for the introduction, Joe, and excited for the invitation to present this webinar. So we're excited to share some of the recent work that we've done utilizing the Bayesian optimizer that we've developed in collaboration with Professor Doyle, who you just heard from. Okay, so at Chemical Process Development at Bristol-Myers Squibb, our mission is to create safe, economical, and sustainable processes to supply high-quality active ingredients for the medicines we deliver to patients. And so that's the lens with which you should view the presentation today. And so when we're developing processes and optimizing reactions, we really have four key pillars: safety, quality, sustainability, and scalability. And so, this is a typical workflow, I think. So we start with, teams, our project teams come up with ideas either as a group or individuals. And then we start to examine these ideas, in a fume hood on the bench. And then when some of those ideas start to gain traction, we explore their reactivity more broadly using high-throughput experimentation. And once we have sort of a narrow set of conditions, we then employ our reaction science workflow to really understand the mechanistic underpinnings of a reaction and understand how everything's working on a fundamental level. And at this point, we tend to have a process, and we engage in a process characterization workflows, things like design of experiment, to really understand what the process risks and liabilities are. And so that's how we go through our optimization cycle. When it comes to exploring reactivity, we've heavily invested in high-throughput experimentation, and there's a couple avenues with which scientists can engage high-throughput experimentation at BMS. We have the specialized designed experimentation group that I'm a part of, which is a dedicated group of subject matter experts to apply HDE across our chemistry portfolio. Things like catalysis screening, class variable screening, design of experiment, solubility measurements, and other physical property measurements. And also, somewhat recently, we have a dedicated data science team within this group to support this work. And also, we have robust end user capabilities. So we want any scientist within our department to be able to use these instruments to accelerate their workflows. So we have a catalysis community of practice for focusing on catalytic transformations, an HDE community of practice just to support the general use of HDE across the department, and a dedicated walk-up automation infrastructure to make HDE available to everybody. And so this is a look at the fleet that we have. So we have a free slate CM3, which is the equivalent of the Unchained Big Kahuna. This supports our highly automated DOE, 9 temperature settings, 3 stir zones, solution transfer, plate and vial, grouping options, 3 powder dispense options. We also have a Unchained Junior, which supports kinetic reaction sampling under inert atmosphere. Also has 6 heat cool stir bays. And then we have a similar free slate CM3, again, similar to the Unchained Big Kahuna, to support our catalysis screening with 6 temperature stir zones, solution transfer, plate transfer, powder dispensing, We have 2 Free Slate Junior PharmDs to support our solubility and crystallization workflow. And then we have a standalone Free Slate Junior powder handler, which has 9 hotel positions to hold 9 96-well plates. Again, 3 powder dispense options. And this is a good walk-up option for our department when they want to use high-throughput experimentation. We also have some Mettler Toledo equipment. We have 2 Cronex to support powder dispensing. We have 2 Mettler Toledo Quantos instruments, which support one-to-many powder dispense. And then we have a Mettler Toledo QX96, which we utilize mostly for the handling of highly potent compounds in 96-well format. And so you can see here, we have quite a few options for laboratory automation. And so, what are the advantages of laboratory automation? And I think when you hear laboratory automation, you think of more experiments and faster. And so that's kind of like the obvious advantages. So when you have all this, the robots that run the experiments for you, you can, take advantage of overnight queues and things like that, run more experiments. And you can also run faster experiments with just the nature of how you do things. I think the less obvious and less appreciated, which I'll highlight today, is that when you're using automation equipment, you have standardized protocols that are inherently reproducible. So the robots are executing transformations for you, and they do so the same way every time. And so this can be an advantage to the system. And also the programmatic nature of laboratory automation. The instruments are only going to do what you tell them to do. So as long as you wrote the instructions properly, they can execute very complex experiments with a low chance of error. And so a theme of my talk today is the programmatic execution of dense and complex experimental arrays is a critical value driver for laboratory automation. And I hope you'll see this in the next handful of slides. So, but first, a brief overview of Bayesian optimization. So Professor Doyle talked about this quite a bit, so I'll only touch on it briefly. Bayesian optimization is a general approach to optimization problems using a response surface-based algorithm. You can optimize categorical and continuous variables at the same time. The great thing about these models is they leverage uncertainty, so they know what they don't know. Our work on EDBO, or experimental design via Bayesian optimization, you can find at the following link and the GitHub page from our collaborator, Ben, who's fortunately now a colleague at BMS. And again, we designed this to be an ideal companion for bench chemistry. It suggests small batches of experiments. And all you really need to run this is to be able to run Python in a Jupyter notebook. And so a key question here is the goal of Bayesian optimization is to find optimized results with fewer experiments. And so you might be wondering, how does this pair with automation? And we'll get to that soon. So in our publication from earlier this year, we detailed this Mitsunobu reaction. So you can see here that this is the reaction that we're optimizing. And so we designed EDBO to take input from the subject matter expert or chemist. In this case, it was me. So I've run Mitsunobu reactions before. And based on my experience, I know that there's 6 reagents, azadircarboxylates, that I think would be appropriate to evaluate. And I came up with 12 phosphines. And for each of these, I decided that these were the equivalents that were appropriate for these discrete variables. I thought there's potentially 5 solvents that would be of interest. And I picked these 3 concentrations. And again, 5 temperatures you see here. So when you add everything up, it's 180,000 possible reaction configurations. And again, I'm in full control of what gets screened. So we're taking knowledge from the subject matter expert to get started. And so once you've decided this, the next thing you have to do, and Abby touched on this, is you have to featureize your data set, which means you have to convert all your categorical variables to numerical features. So in our case, it's the azadircarboxylate reagent, the phosphine, and the solvent. So we have to describe these numerically somehow. And the way that you can do this is you can do things like density functional theory calculations. You get things like HOMO, LUMO, buried, total buried volume, things like that. Or you could convert them to molecular fingerprints, which is essentially a description of what functional groups are present and in close proximity within the molecule. You can use cheminformatics descriptors. In our case, Mordred is part of the EDBO EDBO package. It's a free open source cheminformatics library in Python. You can use other things as well. And the choice is actually pretty important. So this was highlighted in an article by the Coley group that although its importance might be less apparent, the choice of representation, i.e. Featureizing your data set, is as or more significant than the choice of regression model for machine learning. So a lot of time, I think, could be spent in evaluating on which one of these are best. In our case, we decided to use DFV because I think it's pretty much standard at this point. And so what does this actually look like? So if I wanted to featureize this indole sulfamate here, in this case, I utilized molecular fingerprints in using RDKit in Python. And so you just convert this to its molecular fingerprint. In this case, would be 2048 zeros or ones. And depending on what the structure is, you get a different array of zeros or ones. And so that's just a quick example of how featureization works. And so now that you've featureized your data set, you've either collected all your DFT or you got your cheminformatics descriptors for your categorical variables. You then build out the entire featureized data set. So you essentially expand the grid for the 180,000 possible experiments. You get a big data frame that has a list of all the conditions, and then you simply join on your features for your discrete variables. So once you have your complete design space, then you can get started with the software. So in our case, you select your own batch size depending on the equipment you have, what how much time you have that day. You can change this as you go. The process is very iterative and adaptable. So in our case, we selected batches of 10 experiments. And so the first thing you do is you're going to take a random sample from the design space. And then so what we do here is we're just pretty much starting our Bayesian optimizer, and then we're telling it to export the initial proposed experiments is this CSV file, which we can see a readout of here. So we then take this this list of experiments, and then we sort of create an experimental plan and go to the lab and run some experiments. And when you're done, you simply just execute a command like this, bo add underscore results, and then you add the results with the appended column for yield. And that's how you feed information back into the Bayesian optimizer. And again, this is running in a Jupyter notebook with Python. So here's the first real sort of challenge. So we're randomly selecting experiments, and you can totally see that by looking at this. So 10 suggested reactions. So in this set of 10 reactions, we're using 5 different reagents, 7 different phosphines, 4 solvents, 4 different reagent equivalents, 3 different phosphine equivalents, 4 temperatures, and 3 concentrations. So this is a handful to set up in the lab. And so we need a way to be able to do this essentially without screwing it up. And so that's what the main focus was initially is how do we do this without getting distracted or losing our place and sort of making sure that we set this up properly. And that's one of the advantages of automation is you write a program and the instrumentation does exactly what you tell it to do. So at the beginning, we're calculating yields based on response versus an internal standard. So we take a stock solution of our internal standard, pipette that into vials, and then use in this case, a Genovac to remove the solvent. Then we can take advantage of our automation equipment, whereas we can take our indole and phosphine and use our powder dispensing capabilities on, in this case, the free slate CM3, dispense those to the appropriate vials. Once that's done, we then add the appropriate solvent to each vial and equilibrate the temperature. Our unit has 9 different heat cool stir bays, so we can accommodate the numerous temperatures required for this experiment. Then we add our benzyl alcohol. So step 3, in a separate set of vials, we take our azidicarboxylate reagent. Most of them are solids, so we then again can use our powder dispensing equipment to dispense the azidicarboxylate to their appropriate vials. Again, add solvent and equilibrate the temperature. Then we simply add the reagent vial to the vial of our starting materials and phosphine, and then we let the reactions go on our heat cool stir bays. So the advantages of automation, even when setting up sort of 10 experiments, is in this case, our experimental design was very complicated, but we know that the right materials ended up in the right vials because we programmed it that way. And again, at the end, we also get a readout of what went where, so we can double check. And we also know the right amounts end up in the right files, so you don't have to worry about your colleague coming over asking you how the weekend was and then forgetting where you were um, in your preparation. We also take advantage of the multiple heat cool stir bays. And each set of experiments roughly takes about 90 minutes to get things going in this format. And we think it's a very nice way to execute these experiments. So pretty much what you do is you run your experiments, you get the results, you put them back into the optimizer, which will do its calculations and then um, suggest another batch of experiments, and you just repeat this over and over again. And so you can see here, this is our first batch of 10. We found with the random sampling a result around 75% yield. Batch 2, we then increased the yield to about 90. And then after batch 3, we're at, I think, 97% yield. And then at batch 4, we're now at 99% yield. So we found conditions with azide carboxylate reagent, ADDP, methyl diphenylphosphine, which is a phosphine that you don't typically use, I think, for a Mitsunobu reaction, but actually works really well. 99% yield. And this is important because if you're just sort of to go to the lab and use diad and triphenylphosphine, you're going to end up with 60% yield, which is what we showed in the publication, is that those are what the standard conditions give you. So just to review, EDBO began with random selection. We conducted 4 batches of 10 experiments. Automation really helped us execute sort of these complex and diverse designs, and 99% yield and 0.02% of the total design space. And so, as I showed earlier on in the presentation, we have lots of high throughput experimentation infrastructure at BMS. So how do we merge sort of traditional high throughput experimentation with sort of these new methods that take advantage of Bayesian optimization? And so that's exactly what my colleague Alina Borovica set out to do. She manages the class variable screening workflow at BMS process, and she had this challenging hydrolysis. So we're hydrolyzing methyl ester in the presence of terbutyl ester, but there's also some base sensitive functionality that I'm not at liberty to disclose at this point. So we have to use these somewhat mild hydrolysis conditions using a lithium salt, organic base, solvent, and water. And so Alina did what we normally do for high throughput experimentation studies. She went in and ran things in the high throughput experimentation lab. And then at this point, you can see there's 6 solvents, and the best results were obtained with trifluoroethanol, 90+% yield. So we're done, right? Unfortunately, it doesn't work that way in process development. So we sort of use things like trifluoroethanol to get us information about a transformation, but we're not actually going to scale this up. So even though we got 95% yield, unfortunately, we're never going to develop a commercial process with this. But what I'll clue you into here is that we had a 68% yield with methanol, diisopropylethylamine, and lithium bromide. And so these conditions are significantly greener than using trifluoroethanol. And we thought maybe this is an opportunity to see what EDBO can do in terms of optimizing these greener sets of conditions. And so what Lena did is she took information from the initial high throughput experimentation array. So we were originally using 6 solvents, but now she pared it down to 2. We were originally using 4 bases, but now we're only looking at 3. We were looking at 2 different lithium salts. Now we're only looking at 1. But now we're really going to start to investigate continuous variables. So we're now looking at base equivalents, lithium bromide equivalents, concentration, total amount of water in the reaction, and temperature. And so what we did was we utilized high throughput experimentation to sort of alter or refine our design space for EDBO. And then Alina was going to start with a random sample of 12 and then run successive batches of 14 experiments with the idea of asking the question, can EDBO drive up the yield for greener conditions in methanol? And we found great results with this. 95% yield after 1 random initialization and 2 rounds of 14. So we're using now 5 equivalents of lithium bromide, 2 equivalents of diisopropylethylamine in methanol and water, 95% yield. I don't have the concentration and water volumes listed, but those were also factors as well. So the total experimentation, 196 well plate, one set of 12 experiments and 2 rounds of 14, and we're at 95% yield with conditions that sort of everyone's really happy with. So EDBO was indeed able to identify optimal conditions using a much greener solvent choice. And so this is how we've integrated Bayesian optimization with our automation workflows. We see it as sort of a key tool in being able to execute the complex designs for that Bayesian optimization can present us. And also we can add it as a layer on top of our existing high throughput experimentation capabilities. So we think it carries enormous potential for chemical synthesis. The automation mitigates a complex setup for some of these experiments. Layering EDBO on top of HT can rapidly identify global optima. And we think EDBO is really going to have an impact in the identification of greener and more process-friendly chemistry. And with that, I'd just like to acknowledge our data science team, who is an important part of this work, our CPD leadership, our project team collaborators, as well as our Princeton collaborators. And thanks for the opportunity to present today and for your attendance. And I'd be happy to answer any questions in the following Q&A session.
Thanks, Jay, for your presentation. First, we have some great questions that have already come in. If you reminder, you can still ask a question in the Q&A bar by typing it in hit the Q&A and then type it in the Zoom navigation bar. So the first couple of questions I have are for Professor Doyle. One is, what are the directions that you could pursue for improving the Bayesian optimization for chemistry?
There are a number of different things that we've been thinking about here. One sort of that's very sort of practical and certainly derives from needs in my own lab, but I think is something that's general, is when we optimize reactions, we often are optimizing sort of multiple objectives, not just yield, but for example, yield and an anti-selectivity, or yield and price of reagents, or something related to the sustainability or greenness of the reaction. And so there are plenty of examples of doing multi-objective Bayesian optimization outside of chemistry, and so that's certainly something that we're interested in adapting here. And then maybe a more specific to improving the current software is one of the real challenges in this optimization software is early on you have very few experiments and are trying to build this model, this response surface model that relates the chemical structures of the conditions to the yield. And the better that you can make that model approximate the actual objective function, right, the better the optimization is going to be. But that's a real challenge in sort of machine learning, dealing with very few data points. And so things like improving the features, the reaction encoding, or the priors that we put into sort of the response surface model could help ultimately sort of lead to optimizations where you need fewer experiments to get to the highest yielding conditions.
Thank you. The next question I have for you is, what happens if you initiate the computer algorithm with choices made by humans, since these outperform the initial computer choices?
Yeah, so this is an interesting question, and something that we certainly simulated and tried. And what we found is that it doesn't improve the Bayesian optimization to start with the humans' choices, even though they are higher yielding. And that's likely because there's a benefit in either the random selection or using design of experiments principles to initiate the optimization, because it better covers the spreads the surface of the search space, which would allow the algorithm then to have a better sense of where there are pockets of uncertainty, as well as sort of where the yields are, versus humans' choices, which may be more localized in one very narrow area of the search space.
Thank you. Next question is for Jay, which is, what are the best feature sets to use with Bayesian optimization?
Best feature sets. I think I think based on our experiments, our experience, it mirrors, I think, what other people working in machine learning have observed um, in other areas. In that, like, if you can get DFT features, they tend to get you to the answer faster, I believe. But you don't have to use DFT. The cheminformatics descriptors work well, but sometimes you might need to run more experiments because they're not as, I guess, descriptive as the DFT. Um, so I think that's been our experience so far. Yeah.
And next question is Bayesian optimization faster than traditional HTE, and how does access to automation impact the speed of the Bayesian optimization?
Yeah, I think that's a good question, and I think we're in the process of figuring that out. I'm inclined to believe that Bayesian optimization is probably competitive with traditional HTE. So for instance, 196 well play from by the time you think a design, you get a design set up, you plan your experiments, you get your 96 reactions off your UPLC. That's like a 3-day process. A Bayesian optimizer, you get your 10 experiments or however many batches you run, and you could probably get results off your HPLC by the end of the day. So you'll probably run more experiments over a shorter period of time with HDE, but you don't have the benefit of the computer algorithm doing things for you. So I think it's maybe someday we'll have to do the Pepsi challenge, but I think that's a good question.
Okay, thanks. This question is probably for either or both of you to answer, which is for the experimental phase, is there any benefit or loss from running a group of experiments in parallel? So can you learn more by running multiple experiments at once, or is improvement less, or is better improvement per experiment less than running in singleton? And I think there was a related question, which is the Professor Doyle, the work he showed was in batches of 5, and Jay was a smaller format. So I think there's like more of a general question of, well, what's the most effective way to use this? Is it run in a larger format, or to run smaller, or somewhere in the middle?
Right, so it's a good question. We did look at this within our sort of HTE data set for our training sets. So I can speak to what we found there. So generally, running one experiment at a time is going to give the optimizer, right, more information to make sort of the next choices. When you're running 5 experiments at a time, right, it's sort of thinking ahead in sort of the steps. In terms of selecting experiments, 2, 3, 4, 5 for you to run, but it doesn't have as much information as if you were feeding it the results for each of those experiments iteratively. But there is, right, savings in terms of time. And so we did look at this. So you will learn more, and you'll in terms of optimization, it'll take you fewer experiments to get to the highest yield if you do one experiment at a time through the Bayesian optimizer. But if you consider that running each of those experiments takes a day, for example, just to estimate, you have to get results in, versus running 5 experiments or 10 experiments in one batch also takes a day. You can see that it could take you less time to optimize the same point by doing it in batches, is what we found sort of from some of our training data. And in terms of the question of 5 versus 10, versus 96 experiments in a batch, that's not something we have really systematically looked at within the data, but more wanted to provide that flexibility, just depending on the experimental setups that work best for any given user in setting up reactions.
Jay, would you have anything to add to that, in the sense that it kind of depends on what equipment you have and how quickly you want an answer, right? In terms of what the correct batch size is, or is there?
Yeah. I think we're still very much learning. I think now that the question's been presented to me, I don't think we've actually chosen the same thing twice, and I don't know why that is. We've done 5, we've done 10, we've done 8, we've done 12, we've done 14. They have all worked. So I think we haven't found a situation where we haven't been able to use where something's gone awry. But yeah, I think these are sort of somewhat newer tools. and technology, and we're just gonna have to try them out and see how they work. But so far, within like what a typical chemist would set up in the 1 to 20 range, we really haven't observed any this is what you want to do versus this type of scenario.
Okay. And I guess this question's for either one of you or both, which is, how does this compare to design of experiment, which is probably the more traditional way that people are look at optimizing a reaction?
I mean, I can start off, but Jay probably has more hands-on experience with design of experiments than I do. I guess I'd say two things. First, these aren't mutually exclusive. So within the EDBO software package on GitHub, you can choose a design of experiments module to initiate your optimization. So in particular, for selecting the first set of conditions to evaluate design of experiments, I think is a fantastic way to go. The second sort of thing I'd point out, we did make comparisons to using design of experiments in the training data to compare it to the Bayesian optimizer. We chose, I think, we chose de-optimal design and I think generalized subsets to compare to. So, we had to choose design of experiments sort of protocols that are compatible with categorical variables, and not all are. But those were two that we did compare to, and we found that the Bayesian optimizer outperformed those two. And one of the things that we noticed, and again, I'm not a general, I don't practice design of experiments often, but what we noticed is that for multi-level categorical variables, these design of experiments protocols suggest different experiments depending on just the order in which you list the categorical variables. And so the different users might list these differently, and then you're going to get different suggestions for experiments to run. So I think for ease of operation, as well as just overall performance, the Bayesian optimizer we found was more effective.
Yeah, I think what I would add to that is, I agree with everything that Abby said. I think in terms of optimizing a reaction, that the Bayesian optimization tools are probably much more efficient than what you would get with a traditional design of experiment, based simply on the ability to handle categorical variables. And on the other side, so a lot of our design of experiment workflow goes into process characterization to understand process risks and things like that. And I think where I'm at this point is, I think you could use either Bayesian optimization or design of experiment to do that sort of work. So I think the Bayesian optimizer has a lot to offer here.
Thank you both for answering the questions. Unfortunately, we're out of time. There's a lot of other questions that I'm sorry we're not able to get to, but we'll get answers to you offline. Thank you, everyone, for joining us today. And thank you again, Jay and Abby, for your fantastic presentations. If you'd like to have a deeper,
Sorry.
That's right. If you'd like to have a deeper conversation with us about our speakers or the event, please get in touch with us at info@unchainedlabs.com and we'll connect you. If you like the seminar and want to learn more, we do have a series, as I mentioned, coming up already, but also visit the website, unchainedlabs.com, to check out the upcoming events. Thank you all again for your time, and I hope you have a great rest of your day.